go from the
Hello, everyone.
random dots to learn about the highway assessment systems here.
Sure. My name is Vahid. I'm a PhD student working on the 3D reconstruction and recognition for enhanced highway condition assessment. Our research team is Dr. Golpawar, who is the PI of the project, Professor De La Garza, who is the co-PI of the project, me as a PhD student, and Omid, who is a PhD candidate collaborating with the team. The primary research question is to how to recognize and localize highway assets in a 3D image-based point clouds. To achieve this question, we may answer how to generate the 3D model of all infrastructure assets quickly and automatically, how to categorize and segment infrastructure assets in a proper asset categories with reasonable accuracy, how to integrate the recognized categories with the image-based 3D point cloud reconstruction, how to identify the existence and performance deviation and measure the severity-related properties within a reasonable confidence level, and how to visualize the results into a 3D environment. In a recent study which has been done by Dr. De La Garza, he uses the laser scanning for 3D reconstruction. By using the laser scanner, the vehicle speed has a little impact on the quality of data, and also you can collect a large amount of data in a short period of time. But still, the identification of assets in a 3D data needs to be done manually. And also, as you may know, the laser scanner is too expensive. It needs the experts to devise with how to operate with the devices. And this technology suffers from the mixed pixel phenomena and require to remove the noises manually. So the objective of this research is to create, develop, and validate a new method for segmentation and recognition of high-quantity, low-cost highway assets from the video streams and localize them in a 3D environment. High-quantity, low-cost assets including the signs, guardrails, pavement markings, unpaved shoulders, but in this research we just focused on the traffic signs, guardrails, guardrail terminals, and pavement markings. The approach this algorithm, our algorithm has 4 main steps. First, reconstruct a 3D point cloud model using the structure from motion and multi-view stereo. The output of this stage is the 3D point cloud model and also the calibrated camera parameters. Besides that, segment the 2D images at a pixel level into several categories of assets. Using these segmented images combined with the 3D point clouds, color code and label the points in the 3D point cloud, and finally, visualize them in a 3D environment, in an augmented reality environment. To validate our approach, we use the Virginia Tech's Smart Road, which is the state-of-the-art unique research facility, which is managed by the Virginia Tech Transportation Institute. We divided all the infrastructure assets into 12 different types of categories, including asphalt pavements, guardrails, traffic signs, traffic signals, and also assigned a specific color code for each of these categories. We use 70% of these images for training process and 30% for testing. The training process is completely supervised, but the testing is completely automated. Here are some examples for the supervised training. As you can see here, the safety coin, the traffic signs, guardrails with color-coded and generated ground truth based on those color-coded which defined for each of them. And here are the results for segmentation part. As you can see, the safety coin is segmented properly as a blue color, which we define in a training process. Also, the traffic signs segmented properly based on the gray color, which we define for that. For the same for the other type of category of the assets, including the guardrails, traffic lights, safety coins, asphalt pavements. To measure the accuracy for the segmentation, we define 2 types of measurement, 2 types of accuracy of the recognition and accuracy of the segmentation. The average accuracy of this recognition is more than 85% at the pixel level. And for accuracy of the segmentation, we define the confusion matrix, which is a common way in computer vision and computer science side for measuring the accuracy. The average accuracy for segmentation is more than 75%. The big confusion here which we have is between asphalt pavement and the soil, and another confusion is between the concrete pavement and asphalt pavement. The main reason of these big confusions are that the asphalt pavement, concrete pavement, and soil have the same features such as same texture, same color. And also, here we have 100% accuracy for traffic signals, which is segmented properly on all the images. And here are the results for 3D image-based reconstruction. We generated these 3D point clouds based on 66 images. We can generate both a sparse point cloud and also dense point cloud. We can find the location of the camera and which image, we can find out that which image is taken but what kind of camera. Here are some other examples for the 3D image-based reconstruction. As you can see here, the guardrails and safety coins are generating properly in the 3D point cloud. You can walk through the 3D model. You have the bird eye view of highway asset. Also, we can superimpose the real image into the 3D point cloud to see how is the real image with the 3D model is going on. And the final step of this research is generating the 3D segmented point cloud for reconstruction process. Using those segmented images, we generate the 3D point cloud, and we can superimpose the real image to the segmented point cloud and also the segmented images to the segmented point cloud. The final application of this research is to, for example, in AutoCAD, when you are looking for something specific, you can turn off all the layers and turn on that specific layer. Here, based on the images, we can generate a 3D segmented point cloud. You can, if you're, for example, looking for a guardrail condition, you can turn off all the layer and turn on the guardrail layer and look for some specific locations which needs to be maintenance or to replacement. The contribution of this research is the new algorithm for 2D segmentation of assets based on the powerful text on codebooks, without computing the expensive filter banks and descriptors, without performing the costly k-means clustering and nearest neighborhood assignments. Also, the new improved algorithm for 3D reconstruction, which is much more faster compared to the previous versions. The main contribution of this research is the new algorithm for a combination of the 3D reconstruction and asset categorization, which enables assets to be localized in a 3D environment. And also, we generate a new dataset for benchmarking performances. The dataset is uploaded in the Virginia Tech library, and the others can access to these datasets for their testing or for benchmarking purposes. The practical significance of this research is the grand challenge which is identified by National Academy of Engineering in 2010 in restoring and improving the urban infrastructures is devising the techniques which can efficiently create the locations and up-to-date status of highway infrastructures, not only to the existing projects but also affecting the new projects. So there is a lack of techniques to easily and quickly track, analyze, and visualize the actual status of highway infrastructures and monitor the performance matrices. Compared to other technologies, this technology doesn't add any new tasks to the project management. It's easier, cheaper, and much more safer for implementation. It enables the more frequent assessment for infrastructure assets, and also there is no need for experts to operate with the devices. As long as you know how to take the pictures and put the images into the algorithm, you can run the algorithm, and it communicates the information easily between all the stakeholders. The current research proposes a new pipeline for segmentation and recognition of highway assets, but it doesn't fully recognize and classify different types of assets, and also it doesn't distinguish the intra-class variability in the assets. For example, the algorithm detects that this is the traffic sign. What type of traffic sign? Is it a speed limit sign or a stop sign? Also, after the detection and recognition of the traffic signs, how to evaluate the loss of retroreflectivity in traffic signs. In the current work, the user can localize the assets in a supervised fashion. Also, as I mentioned before, the training process is completely supervised, so it's time-consuming and labor-intensive, and there is a need for automated or semi-supervised techniques which can generate the ground truth images for the training process. Also, the automated superparsing algorithm to efficiently segment the highway assets from the 2D images and localize them in a 3D environment. And there is a need for more studying. There is a need for more studying on the impact of the level of the travel speed on the accuracy of the detection of the highway assets. Based on these open research problems, we have submitted some proposals to the NSF, and some of them, we will propose some of them to the NSF. Omid, who is a PhD candidate working with the team, will explain in the next slides to how to evaluate the loss of retroreflectivity in the traffic signs. Omid.
Thanks, Vahid. As Vahid mentioned, one of the As I mentioned, one of the future works is evaluation of signs retroreflectivity measurement. The objective of this work that I'm working on this is measuring the retroreflectivity of traffic signs in daylight. As you might know, measuring the retroreflectivity of signs commonly are being done in night because it's in night that it's visible how much the signs are retroreflective or are not. But the work is significant because we are having lots of data being captured in daytime, and if we are able to analyze and condition assess the signs in terms of retroreflectivity in the daytime captures, we will be able to use the daytime data. The methodology for this is visual nighttime and daytime inspection on the same section. We're having the same section, we do the daytime and nighttime inspection, and then measuring retroreflectivity of traffic signs in nighttime using current technology. We are having the state-of-the-art technologies for measuring in the nighttime, and then train the database on nighttime measured retroreflectivity for daytime measurement using the machine learning algorithms that had been used and they're existing in the work, and then measure retroreflectivity of traffic signs in daytime based on the albedo algorithm, which is an algorithm of detecting the retroreflectivity, and finally developing daytime retroreflectivity measurement for other highway assets. It means that being able to measure this retroreflectivity in daytime is not limited only to traffic signs. There are other asset items in highways that they need to have retroreflectivity, and having this ability will make us capable of doing the measurement of retroreflectivity. Wahid will be explaining the quad chart in the next slides and wrap up.
Thank you, Omid. In this research project, we have the key collaborations with Virginia Tech Transportation Institute, which provide us the access to the smart road for data collection, and also all the undergrad and grad students in the RAMAC lab. We have 4 publications on this research, 1 journal paper, 2 conference papers, and 1 posters. Based for the future open research problems, we submitted 1 proposal to the NSF, which is highly recommended but not funded last year, and with a little bit modification, we submitted another one this year, which the status of that is in the review. And also, the other key successes of this research is the localized identified assessment in higher precision compared to the other technologies such as GPS. It enables the user to select an asset category of the interest and reduce the search time. The user can either navigate through the geo-registered imagery or conduct a joint observation on point cloud and images in a 3D environment. Improving the condition by 0.01% can result in 200 million of cost savings, and also this technology is fast, easy, and more powerful than the other contemporary methods which are using.